In the vast theater of the cosmos, few performances are as breathtaking and destructive as the explosive deaths of massive stars. Imagine an astronomical spectacle where cosmic titans unleash unimaginable energy, reshaping the very fabric of space and time. Supernovas and hypernovas represent nature's most extreme expressions of stellar destruction, each a testament to the raw, unbridled power that governs our universe. When we compare these cosmic explosions, the difference becomes immediately apparent. A supernova, already a mind-boggling event that can outshine entire galaxies, is like a cosmic atomic bomb, releasing energy that defies human comprehension. But a hypernova? It's an exponential leap beyond, comparable to 1,000,000 such atomic bombs detonating simultaneously, creating a cataclysmic burst of energy that can be detected across billions of light years. Our cosmic journey today will dive deep into these celestial giants, exploring their fundamental differences, examining their incredible energy scales, and understanding their profound impacts on the universe. We'll unravel the mysteries of these stellar explosions that not only destroy but also create, generating the very elements that eventually form planets, stars, and even life itself. The fundamental differences between supernovas and hypernovas are stark. While supernovas occur relatively frequently in stellar populations, hypernovas are rare, extraordinary events associated with the most massive and rapidly rotating stars in the universe. Their energy scales are so different that comparing them is like comparing a firecracker to a nuclear blast. The impacts of these cosmic explosions extend far beyond their immediate stellar neighborhoods. They are cosmic forges, manufacturing elements, triggering star formation, and potentially influencing entire galactic structures. From creating heavy elements essential to life to generating powerful gamma-ray bursts that can be observed across immense cosmic distances, these stellar deaths are not just destructions, they are transformative events that drive the evolution of our universe. So prepare yourself for an epic cosmic journey. We're about to explore the most violent, most fascinating explosions ever witnessed by humanity. A battle of stellar titans that will challenge everything you thought you knew about the universe. Are you ready to explore the extraordinary? Activate your cosmic curiosity, subscribe to Exploring the Universe, and join us on this incredible adventure through the most extreme phenomena in existence. A supernova represents one of the most spectacular and violent events in the universe, marking the dramatic end of a star's life cycle. These cosmic explosions are fundamental processes that reshape stellar environments and play a crucial role in the chemical evolution of galaxies. A supernova is an incredibly powerful and luminous stellar explosion that occurs at the end of a star's life. During this process, a star dramatically ejects most of its material with tremendous energy, briefly outshining entire galaxies and releasing an unprecedented amount of electromagnetic radiation. Supernovas, some of the most powerful and luminous events in the universe, are primarily categorized into two fundamental types based on their physical characteristics and mechanisms. Type I supernovas lack hydrogen lines in their spectra and typically occur in binary star systems. This type is further divided into subtypes Ia, Ib, and Ik. Among these, type Ia supernovas are particularly significant for astronomy because their consistent luminosity makes them reliable tools for measuring cosmic distances. On the other hand, Type II supernovas display hydrogen lines in their spectra and result from the core collapse of massive stars. These explosions occur when stars with masses between 8 and 20 times that of the Sun exhaust their nuclear fuel, often leaving behind neutron stars or stellar black holes. Supernovas are relatively frequent in the universe. In a galaxy like the Milky Way, scientists estimate that approximately 2 to 3 supernovas occur per century. Across the observable universe, roughly 100 billion supernovas take place each year, making them a common yet spectacular phenomenon. Most galaxies experience a supernova explosion every 50 years, highlighting their significant role in galactic evolution. The stars that trigger supernovas are typically massive, with masses ranging from 8 to 20 times that of the Sun. They are often part of complex stellar systems, particularly binary configurations, and represent some of the most massive and evolutionarily advanced stars in stellar populations. These stellar progenitors undergo dramatic and catastrophic transformations, leading to their explosive demise. The physical mechanism of a supernova involves the gravitational collapse of the star's core, a sudden and catastrophic release of gravitational potential energy and rapid fusion processes. This explosive energy release ejects stellar material at velocities approaching 10% of the speed of light, producing the brilliant display associated with these events. Supernovas play a critical role in the cosmos. Far from being merely destructive, they serve as cosmic engines that distribute heavy elements like iron, oxygen, and calcium throughout the universe, seeding the formation of new stars and planets. These explosions also provide essential data for understanding stellar evolution and measuring cosmic distances. By studying supernovas, scientists gain deeper insights into the life cycles of stars, the chemical enrichment of the universe, and the expansion of space itself, making these explosive events fundamental to our understanding of the cosmos. These extraordinary stellar deaths represent nature's most powerful recycling mechanism, transforming massive stars into the fundamental building blocks that eventually form planets, stars, and potentially even life itself. Hypernovas represent the most extreme and violent stellar explosions known in the universe, standing at the pinnacle of cosmic destruction. These extraordinary events are far more powerful and rare than traditional supernovas, representing the ultimate expression of stellar death for the most massive stars in existence. A hypernova is a hyperluminous stellar explosion characterized by energy releases exponentially greater than standard supernovas. These cosmic events occur when extremely massive stars, typically those over 30 solar masses, undergo catastrophic core collapse, generating immense energy outputs that can be detected across billions of light years. Hypernovas distinguish themselves through several remarkable features. They are associated with rapidly rotating, massive stars possessing intense magnetic fields. Unlike standard supernovas, hypernovas generate powerful relativistic jets that can penetrate the stellar envelope, creating narrow beams of extraordinary energy. The most distinctive aspect of hypernovas is their production of gamma-ray bursts, potentially the most energetic electromagnetic events in the observable universe. These bursts can release more energy in a few seconds than our Sun will produce throughout its entire lifetime. Hypernovas are exceptionally rare astronomical phenomena. While supernovas might occur several times per century in a galaxy, hypernovas are estimated to happen only once per million years in a typical galaxy. Their extreme rarity stems from the specific stellar conditions required. Massive stars with precise rotational characteristics and magnetic field configurations. Statistically, less than 0.0001% of stellar deaths result in a hypernova, making these events the cosmic equivalent of a once-in-a-civilization occurrence. Each hypernova represents a unique cosmic moment where the fundamental laws of physics are pushed to their absolute limits, creating a spectacle of unimaginable violence and energy that reshapes entire regions of space. These cosmic titans remind us that the universe contains processes of such immense scale and power that they challenge our fundamental understanding of stellar physics and cosmic evolution. Supernovas release approximately 10 under 44 joules of energy, an almost incomprehensible amount that can momentarily outshine entire galaxies. However, Hypernovas dramatically escalate this energy release to 10^47 joules, a magnitude increase that fundamentally transforms our understanding of stellar explosions. To contextualize this extraordinary energy release, consider this compelling analogy. A hypernova generates in mere seconds the total energy output our sun would require billions of years to produce. This means that in the brief moment of a hypernova's explosion, more energy is released than our star would generate throughout its entire multi-billion-year lifespan. A supernova releases approximately 10 quadrillion joules of energy. A hypernova, in contrast, releases approximately 10 octillion joules of energy. The difference between the two is a staggering 1,000-fold increase in energy release. This energy scale represents not just a quantitative difference, but a qualitative transformation in cosmic explosive potential, highlighting the extreme physics governing the most massive stellar deaths in our universe. Supernovas emerge from a specific category of stars with masses ranging between 8 and 20 times the mass of our Sun. These massive stellar objects represent the most promising candidates for explosive stellar death, embodying the critical transition point where stellar evolution culminates in spectacular cosmic destruction. Stars in this mass range undergo complex evolutionary processes that inevitably lead to their dramatic demise. As they exhaust their nuclear fuel, their internal structures become increasingly unstable. The core begins to collapse under its own immense gravitational pressure, triggering the supernova explosion that will scatter stellar material across vast cosmic distances. Binary star systems play a crucial role in supernova formation. In these intricate celestial partnerships, one star can dramatically influence the evolutionary trajectory of its companion. Some supernovas result from interactions within these binary systems, where mass transfer or direct stellar collisions can precipitate the explosive event. The most common progenitor scenario involves a massive single star that has depleted its nuclear fuel. As the star's core collapses, it creates a sudden, catastrophic release of gravitational potential energy. This process generates temperatures and pressures so extreme that they trigger an instantaneous, violent explosion that tears the star apart and releases an unprecedented amount of energy into the surrounding space. These stellar progenitors represent a critical phase in stellar evolution, serving as cosmic factories that forge heavy elements and redistribute material essential for the formation of future stars, planets, and potentially even life itself. Each supernova is a transformative event that marks both the death of a star and the birth of new cosmic possibilities. Hypernova progenitors represent the most massive and extreme stars in the universe, with masses exceeding 30 solar masses. These cosmic giants are characterized by three critical attributes that set the stage for their apocalyptic final moments. Stars larger than 30 solar masses possess sufficient mass to create the extraordinary conditions necessary for a hypernova. These stellar behemoths are rare cosmic specimens, representing less than 1% of stellar populations in most galaxies. Their immense size creates internal pressures and temperatures that push the boundaries of stellar physics. Extremely fast rotation is a fundamental prerequisite for hypernova formation. These stars spin at incredible velocities, often approaching 1,000 kilometers per second at their equators. This rapid rotation generates complex internal dynamics that contribute to the hypernova's explosive potential, creating conditions for generating powerful relativistic jets that can penetrate the stellar envelope. Hypernova progenitors possess magnetic fields millions of times stronger than typical stellar magnetic environments. These intense magnetic structures play a crucial role in channeling energy and generating the narrow, powerful gamma-ray bursts characteristic of hypernovas. The magnetic field's complexity directly influences the explosion's characteristics and energy distribution. The cosmic battle of stellar explosions rages on, we invite you to dive deeper into this astronomical adventure. Are you captivated by the raw power of these celestial events? We challenge you. Which of these cosmic explosions do you find most fascinating? Share your thoughts in the comments below. Don't forget to subscribe to Exploring the Universe. Hit that like button. Join our cosmic community of curious explorers. Supernova explosions are driven by two primary mechanisms: core collapse and uncontrolled fusion, creating a catastrophic stellar destruction process that reshapes cosmic environments. When massive stars exhaust their nuclear fuel, their cores become unable to generate sufficient internal pressure to counteract gravitational forces. This results in a sudden, dramatic gravitational collapse, where the stellar core implodes within seconds. As the core contracts, temperatures and densities reach extraordinary levels, triggering a violent rebound effect that explosively ejects the star's outer layers. During the collapse, remaining stellar material undergoes rapid, uncontrolled nuclear fusion processes. Elements like carbon, oxygen, and silicon undergo near-instantaneous fusion reactions, generating immense energy and creating elements up to iron on the periodic table. This fusion process happens so quickly and with such intensity that it overwhelms the star's internal structure, causing the spectacular explosion. The entire process transforms the star's entire mass in a matter of moments, releasing energy equivalent to the output of billions of suns and creating a brief, brilliant cosmic event that can outshine entire galaxies. These mechanisms represent nature's most extreme method of elemental production and stellar recycling. Hypernova explosions represent the most extreme stellar death events, characterized by three critical mechanisms: rotational collapse, relativistic jets, and black hole formation. Massive stars, spinning at incredible velocities, undergo a unique collapse process. The star's rapid rotation creates complex internal dynamics where gravitational forces interact with centrifugal forces. As the core collapses, this rotational energy becomes concentrated, generating extraordinary pressures and temperatures that drive the hypernova's explosive potential. The most distinctive feature of hypernovas is the generation of powerful relativistic jets. These narrow beams of energy emerge from the collapsing stellar core, moving at velocities approaching the speed of light. These jets can penetrate the stellar envelope, creating extremely powerful gamma-ray bursts that can be detected across billions of light-years. Unlike standard supernovas, hypernovas invariably result in black hole creation. The immense mass and energy of the progenitor star ensure that after the explosion, a stellar mass black hole remains. This black hole represents the ultimate cosmic transformation, a region of space-time where gravitational forces become so intense that not even light can escape. These mechanisms make hypernovas the most violent stellar events in the known universe, representing a cosmic spectacle that pushes the fundamental limits of stellar physics. Supernova explosions are cosmic foundries that generate and distribute critical elements throughout the universe, with a specific focus on element production up to iron. During a supernova, nuclear fusion processes rapidly generate elements from lighter atomic structures up to iron on the periodic table. This process occurs through intense heat and pressure, creating a complex cascade of nuclear reactions that transform stellar material into diverse elemental compositions. Supernova explosions leave behind remarkable astronomical remnants, each with unique characteristics and profound scientific significance. One key remnant is the neutron star, an incredibly dense core composed almost entirely of neutrons. These stars are so compact that a single teaspoon of neutron star material would weigh billions of tons. They rotate rapidly, often completing several hundred rotations per second, and possess intense magnetic fields, making them some of the most extreme objects in the universe. Another remnant is the stellar debris. a rapidly expanding shell of material ejected during the explosion. This debris contains elements synthesized in the supernova, such as iron, gold, and uranium, which are critical to the chemical enrichment of the universe. The expanding material forms intricate nebula structures, like the iconic Crab Nebula, which are visible across vast cosmic distances and provide valuable insights into the mechanics of stellar death. A subset of neutron stars, known as pulsars, is formed when these remnants emit periodic beams of electromagnetic radiation due to their rapid rotation and powerful magnetic fields. These rotating cosmic lighthouses can be detected from Earth as regular pulses of radiation, serving as precise cosmic clocks and beacons that illuminate the remnants of the supernova explosion. Pulsars also provide a unique laboratory for studying extreme physics, including the behavior of matter under intense gravitational and magnetic forces. These products represent critical mechanisms for elemental distribution, playing a fundamental role in the chemical evolution of galaxies and the potential formation of future stellar systems. Hypernova explosions are extraordinary cosmic events that forge elements far heavier than iron, shaping the universe's chemical diversity. These massive explosions drive the rapid neutron capture process, or R process, producing elements like rare earth metals, platinum, and actinides such as uranium and thorium. Even transuranic elements, those heavier than uranium, can form in these extreme conditions, marking hypernovas as the origin of some of the universe's most complex atomic structures. A key aftermath of a hypernova is the formation of a stellar mass black hole, one of the universe's most enigmatic entities. These black holes possess gravitational fields so intense that not even light can escape. They often consume nearby stellar material, creating accretion disks that can emit powerful X-rays. In some cases, the dynamics of their formation may generate gravitational waves, ripples in space-time that provide profound insights into these cataclysmic events. Black holes formed in hypernovas also play crucial roles in galactic evolution, influencing star formation and the distribution of matter. Another hallmark of hypernovas is the generation of gamma-ray bursts, the brightest electromagnetic events in the universe. These bursts consist of extraordinarily narrow beams of high-energy gamma rays that can last from milliseconds to several minutes. GRBs are detectable across billions of light-years, serving as cosmic lighthouses that illuminate the farthest reaches of the universe. Their immense energy output and extreme luminosity make them essential tools for studying the early universe and understanding the most violent phenomena in existence. Hypernovas, through their production of heavy elements, black holes, and gamma-ray bursts, are fundamental to shaping the cosmic landscape and advancing our understanding of the universe. These products fundamentally transform cosmic environments, generating the complex elements necessary for planetary formation and potentially seeding the conditions for future stellar and planetary systems. Supernovas act as powerful agents of transformation within their local stellar environments, reshaping their surroundings through the distribution of newly forged elements. These explosions inject heavy elements, such as iron, oxygen, and silicon, into nearby interstellar space, enriching the region's chemical composition. The intense energy released creates shock waves that compress gas and dust, forming dense molecular clouds capable of initiating new rounds of star formation. This process helps recycle stellar material, ensuring the continual birth of stars and the enrichment of galactic neighborhoods with complex chemical structures. Hypernovas, on the other hand, are cataclysmic events with far-reaching consequences that extend across entire galaxies. These colossal explosions distribute heavy elements on a massive scale, significantly enriching multiple star-forming regions. The scale of their chemical contributions profoundly influences the galactic ecosystem, introducing rare and heavy elements such as gold, platinum, and uranium, which are essential for forming complex planetary systems and potentially life. In addition to their elemental contributions, hypernovas impact galactic evolution through their immense energy output. Their explosive force can create widespread shockwaves, compressing vast regions of interstellar material and potentially triggering star formation on a galactic scale. The gamma-ray bursts produced by hypernovas, among the most luminous events in the universe, are detectable across immense cosmic distances and can provide critical insights into the structure and behavior of the early universe. These transformative events play a pivotal role in shaping the evolution of galaxies, influencing their chemical, structural, and dynamic properties over billions of years. While supernovas create localized transformations, hypernovas function as cosmic reset mechanisms. Supernovas enrich stellar neighborhoods. Hypernovas fundamentally reshape galactic chemical compositions and potentially trigger large-scale structural changes in cosmic environments. These extraordinary stellar deaths serve as critical mechanisms for universal chemical evolution, generating the fundamental building blocks necessary for future stellar and planetary formation. Supernovas and hypernovas represent the most luminous events in the universe, with remarkable brightness achievements that challenge our understanding of cosmic illumination. The most luminous supernova ever recorded, SN 2006G, outshone its entire host galaxy, releasing energy equivalent to 100 billion suns. This extraordinary event demonstrated that stellar explosions could reach unprecedented levels of brightness. Hypernovas take luminosity to an even more extreme level. The gamma-ray burst, GRB 080319b, observed in 2008, was so bright that it could theoretically have been visible to the naked eye from Earth for several seconds, despite occurring billions of light-years away. This event released more energy in a few moments than our Sun will produce throughout its entire 10-billion-year lifetime. The scientific understanding of these cosmic explosions has a fascinating history. The first supernova observed in detail was SN 1054, which created the Crab Nebula. Chinese astronomers recorded this spectacular event in 1054 AD, noting a guest star that remained visible for 23 days. This historical observation became crucial in understanding stellar evolution. Hypernovas were first theoretically proposed in the late 1990s, with the first comprehensive observations coming in the early 2000s. The discovery of long-duration gamma-ray bursts fundamentally transformed our understanding of the most extreme stellar deaths in the universe. Recent astronomical observations continue to provide extraordinary insights. In 2022, astronomers detected a hypernova event that generated one of the most powerful gamma-ray bursts ever recorded. The event, labeled GRB 221009A, was so intense that it was dubbed the Boat, creating unprecedented scientific excitement. Another remarkable recent observation was the supernova SN 2016 IET, which showed unusual characteristics that challenged existing stellar explosion models. This event suggested that some supernovas might have more complex formation mechanisms than previously understood. The frequency of these cosmic events provides a stark contrast. Supernovas occur relatively frequently, with approximately 2 to 3 happening in the Milky Way every century. Across the observable universe, roughly 100 billion supernovas happen annually. Hypernovas, however, are extraordinarily rare. Estimates suggest that only one hypernova occurs per million years in a typical galaxy. This extreme rarity makes each observation a momentous scientific event, offering researchers precious opportunities to study these cosmic titans. These curiosities illuminate the breathtaking scale and complexity of stellar explosions, reminding us that the universe continues to surprise and challenge our scientific understanding with each extraordinary observation. Dr. Elena Rodriguez, astrophysicist at the International Stellar Research Institute, emphasizes the transformative nature of these cosmic events. Supernovas and hypernovas are not just destructive phenomena, but the primary mechanisms through which the universe creates and distributes complex elements. They are essentially the cosmic recycling system that makes planetary formation possible. Dr. Michael Chen, lead researcher at the Global Astronomical Observatory, provides a comparative perspective. While supernovas are remarkable, hypernovas represent the ultimate expression of stellar death. They are so rare and powerful that each observation is like discovering a new fundamental law of physics. The scientific community is currently engaged in several intense debates surrounding these stellar explosions. Progenitor diversity. Researchers are challenging traditional models of stellar evolution, arguing that the conditions producing hypernovas might be more complex than previously understood. There's ongoing discussion about the precise stellar characteristics that trigger these extreme events. Energy distribution mechanisms. Scientists are exploring the intricate ways energy is generated and distributed during hypernova events. The generation of relativistic jets and their interaction with surrounding stellar material remains a critical area of investigation. Black hole formation. Theories. The relationship between hypernova explosions and black hole creation is generating significant scientific discourse. Researchers are attempting to develop more precise models, explaining how these massive stellar deaths result in black hole formation. Several groundbreaking theories are currently reshaping our understanding of stellar explosions. Quantum gravitational models. Some theoretical physicists propose that hypernovas might provide unique insights into quantum gravitational interactions. These models suggest that the extreme conditions during these explosions could reveal fundamental properties of space-time. Multi-messenger astronomy. A new approach combines gravitational wave detection, electromagnetic observations, and neutrino measurements to create a comprehensive understanding of stellar explosions. This integrated methodology promises unprecedented insights into these cosmic events. Cosmic chemical evolution theories. Researchers are developing more sophisticated models explaining how supernovas and hypernovas contribute to the chemical enrichment of galaxies. These theories suggest that these stellar explosions play a more nuanced role in universal elemental distribution than previously conceived. Dr. Samantha Williams, a leading theoretical astrophysicist, offers a thought-provoking perspective. Each hypernova we observe is like a window into the most extreme physical processes in the universe. These events challenge our fundamental understanding of matter, energy, and the very fabric of space-time. The ongoing scientific exploration of supernovas and hypernovas continues to push the boundaries of human knowledge, offering tantalizing glimpses into the most violent and transformative processes in our cosmic environment. The universe contains phenomena so extreme that they challenge our fundamental understanding of physical reality. Hypernovas represent the pinnacle of cosmic violence, stellar explosions that transcend traditional astronomical boundaries and push the limits of known physics. While supernovas are already mind-boggling events that can outshine entire galaxies, hypernovas elevate cosmic destruction to an almost incomprehensible scale. These stellar deaths are not merely explosions, but transformative events that fundamentally reshape space-time itself. Consider the extraordinary energy release. A hypernova generates more energy in mere seconds than our sun will produce throughout its entire multi-billion-year existence. The violence of these events is so profound that they create narrow beams of radiation capable of penetrating billions of light years, generating gamma-ray bursts that represent the most energetic electromagnetic events in the observable universe. The formation of a hypernova involves stars over 30 solar masses spinning at incredible velocities, often approaching 1,000 kilometers per second at their equators. These cosmic titans possess magnetic fields millions of times stronger than typical stellar environments, creating conditions so extreme that they challenge our understanding of fundamental physical laws. When a hypernova occurs, it's not just a stellar death, it's a cosmic reset mechanism. These events generate elements heavier than iron, create stellar mass black holes, and potentially influence entire galactic evolutionary trajectories. The relativistic jets produced can penetrate stellar envelopes with such intensity that they create phenomena observable across unimaginable cosmic distances. The true significance of hypernovas lies not just in their destructive potential, but in their creative power. They are cosmic crucibles that forge the complex elements necessary for planetary formation, potentially seeding the conditions for future stellar systems. In this sense, these ultimate stellar explosions represent both destruction and creation, a violent poetry written in the language of fundamental physics. Ultimately, hypernovas remind us that the universe contains processes of such immense scale and power that they challenge our most fundamental scientific understanding. They are not just astronomical events, but cosmic symphonies that play out at the very edges of physical possibility, where the fabric of space-time itself becomes a canvas for unimaginable transformation. Supernovas and hypernovas are the universe's primary element manufacturing facilities. These stellar explosions create nearly all elements heavier than hydrogen and helium. Through intense nuclear fusion and rapid neutron capture processes, they synthesize carbon, oxygen, nitrogen, and metals essential for planetary formation. Our bodies are direct evidence of this cosmic alchemy. Every atom of calcium in our bones, iron in our blood, and carbon in our DNA originated from stellar explosions. We are, quite literally, composed of recycled stellar material generated through these extraordinary cosmic events. These stellar explosions are fundamental to life's possibility. Without the elemental distribution created by supernovas and hypernovas, planetary formation would be impossible. The complex chemical environments required for biological development depend entirely on these cosmic crucibles. Moreover, the energy and matter dispersed by these explosions trigger new star formation, creating the astronomical conditions necessary for planetary systems to emerge. Each supernova and hypernova represents a critical step in the evolutionary chain that ultimately led to our existence. Emerging research focuses on several groundbreaking areas. Gravitational wave detection. Advanced instruments will allow precise measurement of stellar explosion dynamics. Multi-messenger astronomy, combining electromagnetic, gravitational, and neutrino observations. Quantum gravitational models, understanding extreme physical conditions during stellar deaths. Exoplanet formation mechanisms, tracking elemental distribution's role in planetary system creation. Scientists anticipate that future observations will provide unprecedented insights into the universe's most violent and transformative processes, potentially revealing fundamental laws of physics currently beyond our comprehension. In the grand theater of the universe, supernovas and hypernovas are not competitors, but complementary cosmic performers, each playing a crucial role in the ongoing drama of universal evolution. These stellar explosions are more than mere destructive events. They are the fundamental mechanisms of cosmic creation and transformation. Supernovas, occurring more frequently, serve as localized cosmic forges. They distribute elements up to iron, enrich stellar neighborhoods, and trigger star formation in their immediate galactic regions. These explosions are the workhorses of elemental distribution, creating the chemical foundations for future stellar systems. Hypernovas, rare and extraordinarily powerful, represent the ultimate expression of stellar death. They generate elements beyond iron, create stellar mass black holes, and potentially reshape entire galactic structures. Their gamma-ray bursts can be detected across billions of light-years, serving as cosmic beacons that reveal the most extreme physical processes in the universe. Together, these cosmic titans are responsible for creating the very elements that compose our existence. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were forged in the nuclear furnaces of dying stars. In this sense, we are quite literally made of stardust, born from the violent deaths of cosmic giants. Your journey into the universe's most extreme phenomena has just begun. We invite you to dive deeper into the mysteries of stellar explosions. Subscribe to Exploring the Universe. Activate notifications to never miss a cosmic revelation. Engage with our content by liking and sharing. Join our community of curious cosmic explorers. The universe is waiting to be discovered, one stellar explosion at a time.